This video is sponsored by Squarespace, the big bang of website builders. Have you ever wondered why time seems to flow in only one direction? Why people grow old and die? Why buildings decay? Why eggs fall and shatter, but never seem to reassemble? And why waves crash onto beaches, but beaches don't suddenly launch waves back out to sea? If you watch a movie of everyday life played backwards, you usually notice instantly because something feels deeply unsettling and unnatural when familiar processes run in reverse. But now take a movie of two individual particles colliding and play it backwards, and you can't tell which way time is running. At the microscopic level, the motion looks perfectly fine either way, and that's not an accident. When you look at the laws of physics themselves, the directionality disappears. You see, Newtonian mechanics, quantum mechanics, and even relativity, in most cases, work just as well with time running backwards as they do with time running forwards. The equations don't contain an arrow that says, this way is the future. So if time's arrow is not built into the underlying equations of physics, where does it actually come from? Well, the surprising answer has very little to do with the laws themselves. It has to do with the way the universe began, with the Big Bang, and the state that it started in. And when you actually do the numbers, you find something extraordinary. The beginning of our universe turns out to have been so special, so finely balanced, that the odds of getting something like it by chance are about 1 in 10 to the power of 10 to the power of 123, a double exponent. Today I want to show you where that insane number comes from, and why it helps explain why time in our universe has a direction at all. To make sense of this, we need one of the most important ideas in physics, entropy. And to find it, we have to go back to the late 19th century to a physicist named Ludwig Boltzmann. Boltzmann's key insight was that the arrow of time isn't something the laws of motion put in by hand. Rather, it emerges from counting how many microscopic ways a system can be arranged such that some macroscopic feature still looks the same. And the concept that captures this counting is entropy. Once you look at time this way, the mystery of why things happen one way but not the other becomes a question about probability, about which kinds of states are rare and which kinds of states are overwhelmingly typical. To see what Boltzmann meant by entropy, we'll begin with something very simple, the tossing of a coin. Imagine you toss 100 fair coins. Each coin has two possible outcomes, heads or tails. Now imagine throwing each of the 100 coins one by one. For the first coin, there are two possible outcomes. For the second coin, again two possibilities, and for the third coin, again two choices, and so on, all the way up to the 100th coin. Because these choices are independent, the total number of possible sequences is found by multiplying. Two choices for the first coin, times two choices for the second, times two choices for the third, and so on, repeated 100 times. And this is simply equal to 2 raised to the power of 100. And so we see that the total number of possible sequences, 2 to the power of 100, is roughly equal to 1.27 times 10 to the power of 30. In other words, just 100 coins already give you more than a nonillion different possible sequences of heads and tails. It's an absurdly large number. That's 1 million trillion sequences. If you tried to count these outcomes one by one, at 1 per second, it would take you far longer than the age of the universe just to list them all, and that's with only 100 coins. Now, each of those detailed sequences is what we call a microstate, a complete microscopic description of what happened. But we can also describe the outcome of 100 throws of the coin in another, more coarse-grained fashion. For example, when you look at the outcome, you might say, I got 100 heads, or I got 13 heads and 87 tails, or I got 50 heads and 50 tails. In this case, the number of heads that you get represents what we call a macrostate. A macrostate doesn't tell you the exact sequence of heads and tails. It only tells you some coarse-grained feature of the outcome, like the number of heads you got. Now, here's the crucial point. Different macrostates correspond to wildly different numbers of microstates. For example, there is only one sequence that gives you all heads, so the macrostate all heads corresponds to exactly 1 microstate. Whereas for the macrostate 99 heads and 1 tail, the tail could be in the first position, or the second, or the third, and so on, all the way up to the 100th position. So there are 100 different sequences that look like 99 heads and 1 tail. And so we say that there are 100 microstates corresponding to this macrostate. More generally, if you have n coins and k heads, then the number of sequences corresponding to the macrostate k heads is given by the binomial coefficient, which says that n choose k is equal to n factorial divided by k factorial multiplied by n minus k factorial. So for example, the macrostate 90 heads and 10 tails corresponds to 100 choose 10 microstates, which is equal to 100 factorial divided by 10 factorial times 90 factorial, and this is approximately equal to 1.7 times 10 to the 13 different microstates. Whereas the macrostate 50 heads and 50 tails corresponds to 100 choose 50 microstates, which is equal to 100 factorial divided by 50 factorial times 50 factorial, and this is approximately 1 times 10 to the 29 microstates, a truly staggering number. That's a 1 with 29 zeros worth of sequences. So already we can see something striking. We see that some macrostates, like 100 heads, are incredibly special. There are almost no microscopic ways to realise them, whereas other macrostates like 50 heads and 50 tails are overwhelmingly typical, with unimaginably many microstates corresponding to the macrostate. Now, we can turn this counting into an actual probability. Because the coins are fair, all microstates are equally likely, meaning that the probability of achieving any one sequence is the same as achieving any other. And we've already seen that the total number of microstates is 2 to the power of 100. And so it follows that the probability of a given macrostate is equal to the number of microstates corresponding to that macrostate divided by 2 to the power of 100. That means that the probability of achieving 100 heads is equal to 1 divided by 2 raised to the power of 100, because there is only one microstate corresponding to this macrostate. And this is roughly equal to 1 divided by 1.27 times 10 to the power of 30. Roughly 1 in a million billion billion. So absurdly unlikely that the probability is essentially 0 for all practical purposes. Meanwhile, the probability that we obtain exactly 50 heads is equal to 1 times 10 to the power of 29 divided by 2 to the power of 100, and this is roughly equal to 0.08. That's about 8%. Now, you might not think that this is a very large number, but remember, this represents the chance of exactly 50 heads and 50 tails. But if you calculate the probability that the number of heads lies between 45 and 55, you find a probability of about 73%, and between 40 and 60, it's about 96%. In fact, we can visualize the probability distribution. If you plot the number of heads on the x-axis and the probability on the y-axis, you get a sharply peaked curve centered around 50-50, with the extreme cases living way out in the tiny tails of the distribution. Okay, so now that we've wrapped our head around microstates, macrostates, and counting states, let's ask a real-world question. Why does a gas spread out and then stay spread out? Imagine you could somehow squeeze all the air in the room into one corner and then release it. It would rush out and fill the entire room. That part feels natural, but here's the real puzzle. Why don't we ever see the reverse? Why doesn't the air, once it's spread out, ever spontaneously gather back into a corner again? To answer that properly, we don't actually need the full microscopic description of the air. Instead, we're going to do what physicists always do and replace the messy, real situation with a clean, idealized model that captures the essence of the problem. So let's consider a simple box of gas. Now, once the gas has had time to mix, any given particle at any moment in time has effectively a 50-50 chance of being on either side, and therefore the number on, say, the left side of the box is very well described by the same binomial curve we plotted for coins, sharply peaked near 50-50. So in this simple left-right description, the evenly spread out state is typical because almost every microscopic arrangement looks like this at the macroscopic level. And that's the statistical heart of what we mean by entropy. Before we get back to the physics, a quick note about something I've been building alongside this channel, the Physics Explained website. I wanted a place where all this material could live in a more structured way, courses, extra notes and sets of questions for people who want to go a bit deeper. Squarespace makes that really straightforward. You can organise content into members-only areas, decide what's free and what's behind the scenes, and even offer access as a one-off or a subscription, all in the same site. There are also built-in tools for supporting the project itself, including simple donations that happen right there on the page without extra layers or complicated setup. What I like most is that everything connects together: content, community and support, inside one consistent space, keeping the focus where it should be, on the ideas. If you'd like to try it yourself, head to squarespace.com for a free trial, and when you're ready to launch, go to squarespace.com/physicsexplained to get 10% off your first website or domain. In simple terms, entropy is a measure of how many microscopic states correspond to the same macroscopic description. So a macrostate like all particles on the left has lower entropy than a macrostate corresponding to a 50-50 spread because there are vastly more microstates that look like the second macrostate than the first. So entropy isn't really about messiness or disorder, it's about counting and statistics. It's about how big the space of microscopic possibilities is given what we choose to notice at the macroscopic level. The bigger that space is, the higher the entropy should be. It's why a spritz of perfume spreads through a room like a growing cloud instead of spontaneously gathering back into one corner. Not because gathering is forbidden, but because there are vastly more microscopic ways for it to be spread out than for it to be clumped together. And it's why when you stir two colours of paint together, they mix and never spontaneously unmix. The separated state is very special with relatively few microstates, whereas the mixed state can be realised in vastly more microscopic ways. And so if we want a quantitative definition of entropy, what we need is a single number that grows when the number of compatible microstates grows and shrinks when that number shrinks. And that's exactly what Ludwig Boltzmann discovered. Boltzmann defined entropy with the following simple, elegant equation, where here omega is the number of microstates compatible with the macrostate that you're describing, and k is Boltzmann's constant. But why the logarithm? To answer that question, we need to think about what happens if we want to calculate the combined entropy of two systems. For example, suppose you have two identical independent boxes of gas. Each box has the same entropy, let's call it S, and if you treat them as a single combined system, the total entropy is just the sum of the two, which we can write as 2S. More generally, if the first box has entropy SA and the second box has entropy SB, then the combined system has total entropy equal to SA plus SB. In other words, for independent systems, entropy is additive. But now let's think in terms of microstates. If box A has omega A microstates and box B has omega B microstates, then the total number of microstates of the combined system will be equal to the product omega A times omega B, because for every microstate of box A, box B can be in any one of its microstates. The possibilities multiply. So we have a situation in which microstates multiply, but macroscopically entropy should add, and this is where the logarithm plays its role, because the logarithm turns multiplication into addition. If we take the logarithm of the total number of microstates of the combined system, we can write this as log of omega A times omega B, and this is then equal to log of omega A plus log of omega B. And then if we recall the Boltzmann definition of entropy, then we see that the total combined entropy will be equal to k log omega total. And using our previous result, we see that this is simply equal to SA plus SB, exactly as required. And so now we see why the logarithm is there. It turns multiplication of possibilities into addition of entropies. and Boltzmann's constant just sets the units so that the statistical definition of entropy matches the entropy we already know about from thermodynamics. Now, with that in mind, let's actually watch a gas evolve. We'll start with a box of particles where initially all of them are crammed into the left-hand side, and then we'll let the system evolve according to ordinary Newtonian mechanics. So let's now try to estimate the entropy of this toy left-right model. If n is the total number of particles and nl is the number of particles on the left side of the box, then the number of compatible microstates, omega, is equal to n choose nl, and it then follows that the entropy of our toy model can be written in the following form. This can be thought of as the left-right coarse-grained entropy. It quantifies how typical a particular left-right split of particles is, but it ignores the exact positions, velocities, energies, and so on. So it's not the full thermodynamic entropy of the gas. But as an illustrative toy model, it works nicely. So now if we run the simulation again and plot the entropy, we see that as time goes on, the particles spread out, cross the midline and mix, and the fraction on the left tends towards 1/2. We see the entropy rise and then flatten out, undergoing small fluctuations. Now, the key point is that nothing in Newton's laws is pushing the entropy up. Rather, as the system evolves, it becomes overwhelmingly more likely for the system to remain in the higher entropy state that it finds itself, with a vanishingly small probability of the entropy lowering back down to the value it had when all the particles were on one side of the box. And with this in mind, we can now fully appreciate the second law of thermodynamics. In its simplest form, it says that for an isolated system, entropy tends to increase with time. The key word there is tends. The second law isn't a fundamental law like Newton's laws, it's a statistical law. It's a statement about what almost always happens, not about what is logically forbidden. And this also links to time itself. The arrow of time is simply the direction in which entropy tends to increase, the direction in which systems move from extremely rare special macrostates to overwhelmingly typical ones, like a gas spreading out and never returning to the corner in which it started. If you ever witnessed the reverse, you wouldn't just think it unusual, you would feel that something is deeply wrong. Your intuition would scream. And now you know why. We live in a universe where forwards in time is the direction of increasing entropy, so our brains treat that direction as normal. And that's why it feels strange when the broken egg recombines, or when the apple juice climbs back into the carton from where it was poured. But now let's take the next step. If instead of a box of particles we treat the entire universe as our system, then the same logic applies on the largest possible scale. The entropy of the universe appears to be increasing with time. But if entropy is higher today than it was yesterday or a billion years ago, then the natural conclusion is that the universe itself must have started in a very low entropy state. But now we hit a problem, because as you probably know, there is overwhelming evidence that the universe began with the Big Bang. A hot, dense, violent event that has left a trace we can still see today as the afterglow of the Big Bang. If we look at the sky, not in visible light but in microwaves, we see the entire sky faintly shimmering with that ancient radiation. Light that was emitted when the universe was young and then stretched to longer and longer wavelengths as the universe expanded, until today it sits in the microwave part of the spectrum. And if we measure how the intensity of this radiation depends on the frequency and wavelength, we don't get some random shape, we get a very specific curve, an almost perfect blackbody spectrum. And that tells us something very specific about the state of the early universe. A blackbody spectrum is the unmistakable fingerprint of a system that has reached thermal equilibrium. So what does that mean? Well, when physicists say a system is in thermal equilibrium, they mean that hot regions have shared energy with cold regions. Collisions and interactions have shuffled energy around until the whole system can be described by a single temperature. In that sense, it has forgotten how it started. Think of a box of gas split by a partition, hotter gas on the left, cooler gas on the right. Then remove the partition and the particles collide and exchange energy until the average energy, and therefore the temperature, on both sides equalizes. In this process, entropy increases because there are vastly more microscopic ways for the total energy to be evenly shared between the two halves with a uniform temperature than for the temperature to remain different on either side. So we see that thermal equilibrium corresponds to higher entropy. And this kind of uniformity is exactly what we see when we measure the temperature of the cosmic microwave background radiation across the sky. We find that it's essentially the same in every direction, represented here by the uniform green coloration. It's only when we increase the temperature resolution to about 1 part in 100,000 that we notice tiny variations, shown here by the different colour shading. And so the message from the Big Bang's afterglow is clear. The early universe was astonishingly uniform. And that's the key point. Uniform temperature is what equilibrium looks like. So for matter and radiation, a sky glowing uniformly with microwave radiation is exactly what you'd expect from a system that has reached thermal equilibrium, a state of very high entropy for matter and radiation. Now here's the twist. Imagine a box on truly cosmic scales thousands of light years across, filled with a diffuse cloud of matter. From everything we've said so far, you might think that this must be a high entropy state. After all, it looks like a smooth, uniform distribution of matter. A bit like the end point if we start with the gas concentrated in a box and then release it and allow it time to spread out into a high entropy state. But from a gravitational point of view, it's closer to the opposite. A smooth, uniform mass distribution is actually a low entropy state. The reason is that gravity is attractive, so matter gets pulled together forming clumps, and in a gravitating system, clumping drives entropy up, because collapse releases energy into heat and random motion. And so we see that the behaviour of the gravitating matter is the complete opposite of the behaviour of the box of gas. With an ordinary gas, spread out and uniform is the high entropy end state, but gravity flips that intuition. And in Einstein's general theory of relativity, this gravitational clumping process has an ultimate endpoint. There's a limit to how much mass and energy you can squeeze into a region of space before the region collapses to form a black hole. And thanks to the work of Bekenstein and Hawking, we know that black holes carry an enormous amount of entropy, proportional to the area of their event horizon. For a given amount of mass and energy in a region of space, that means something remarkable. The state of maximum entropy is not a smooth, uniform cloud of matter. It's a state dominated by black holes, and the entropy of such a state is vastly, unimaginably larger than the entropy of the same amount of matter spread out smoothly through space. And so we can now resolve the apparent paradox we encountered earlier, where it appeared that the second law of thermodynamics demanded that the early universe was in a low entropy state, whereas the cosmic microwave background radiation appeared to indicate that the early universe looked like a state of high entropy thermal equilibrium. You see, the early universe looked like it had very high entropy if you only pay attention to matter and radiation and ignore gravity. Whereas from a gravitational perspective, it was an extraordinarily special low entropy state, almost perfectly smooth and uniformly distributed, with enormous scope for future clumping and the formation of structures such as stars, galaxies, and ultimately black holes, the true entropy monsters of our universe. So the obvious next question is, can we quantify this special low entropy state? And the good news is yes, we can. We can start by estimating the entropy near the beginning of the universe by studying the cosmic microwave background radiation. As mentioned earlier, when we measure the CMB's energy distribution as a function of frequency, we find it has a characteristic blackbody curve indicating a state of thermal equilibrium. Now here's the key simplification. For thermal radiation such as this, the total entropy scales with the total number of photons. In other words, we can say that S is proportional to n gamma, where n gamma is the number of photons. And the reason is actually very intuitive. Take two identical boxes of blackbody radiation, same temperature, same volume, so each box has the same spectrum, the same number of photons and the same entropy. Now put them together into one bigger box. Because the two boxes were independent, the total entropy is just the sum. It doubles. And physically, we've simply doubled the amount of blackbody radiation at the same temperature. So doubling the photon number doubles the entropy. And so it follows that for blackbody radiation in thermal equilibrium, each photon carries roughly a fixed amount of entropy, on the order of a few Boltzmann constants, which means the total entropy is simply proportional to the total number of photons. Now let's apply that to the universe. From observations of the cosmic microwave background, combined with measurements of the cosmic baryon density, we know that the universe contains about 1 billion photons for every baryon. And since there are of order 10 to the 80 baryons in the observable universe, the total number of photons, n gamma, is roughly equal to 10 to the 9 times 10 to the 80, which is of order 10 to the 89. And because photons outnumber baryons by about 1 billion to 1, the entropy carried by ordinary matter is tiny by comparison. So to an excellent approximation, the thermal entropy can be approximated by the photon entropy. Then, since entropy scales with photon number, the entropy in the thermal radiation is of order n gamma times k, which is roughly 10 to the power 89 times k. Okay, so this is the entropy we measure corresponding to the thermal radiation of the cosmic microwave background today, but why can we say that this corresponds to the entropy near the beginning of the universe, when the universe has been expanding for billions of years? Well, the reason is because as space expands, each photon's wavelength stretches with it. Longer wavelength means lower energy, so the radiation cools and the temperature drops as the universe expands. If you follow an expanding region of space, two things happen at once. The radiation inside the region cools, which lowers the entropy per unit volume, that's the blue curve, but the region itself gets bigger, which increases the total volume available, that's the orange curve. And for thermal radiation, these two effects balance in just the right way. The result is that the total entropy of the CMB radiation inside that expanding region stays essentially constant, as seen in the final plot. That's why counting the CMB photons and their entropy today is effectively measuring the entropy this region already carried in the early universe. Okay, so let's pause and take stock. We've managed to estimate the entropy of the early universe shortly after the Big Bang, and we found a value of 10 to the power 89 times Boltzmann's constant. And you would be forgiven for thinking that this feels enormous in everyday terms. But remember, the second law of thermodynamics tells us something crucial. The early universe must have been a low entropy state, otherwise entropy couldn't have increased and we wouldn't have an arrow of time at all. So that immediately tells us something important. The entropy of the universe today must be much larger than this seemingly already huge number. So how do we estimate the total entropy of the universe today? Well, as already mentioned, in ordinary gases, uniformity is high entropy. Things spread out, clumps smooth away. But in a gravitating universe, the logic is completely reversed, and gravitationally clumped matter represents high entropy. General relativity then tells us that if you clump enough matter together into a small enough region, a black hole will form, with the entropy proportional to the area of the event horizon. And, as we're about to see, black holes are entropy monsters. To see just how monstrous they are, we can use the fact that for a non-rotating black hole, the Schwarzschild radius is given by the expression 2gm divided by c squared. This represents the radius of the region of the event horizon of the black hole. And so we can then derive an expression for the event horizon area, since the area of a sphere is given by 4 pi r squared. And if we sub in the expression for the Schwarzschild radius, we get the following result. And if you then combine this with the entropy equation, you find something remarkable. The entropy of a black hole scales with the square of its mass. This means that if you double the mass, you don't just double the entropy, you get 4 times as much. Triple the mass, and you get 9 times as much. So the bigger the black hole, the greater the entropy and the more it dominates the entropy of everything around it. And this raises a natural question. Where are the biggest black holes in the universe today? And can we estimate their entropy? Because if these really are the entropy monsters the equation suggests, then they will utterly dominate the entropy of the universe today. Well, you may remember back in 2019, the Event Horizon Telescope released the first ever image of a black hole, the supermassive black hole lurking at the centre of the M87 galaxy, about 55 million light years from Earth. What you're seeing isn't the black hole itself, but its dark shadow set against a glowing ring of superheated gas. This supermassive black hole is a true monster, with a mass of roughly 6.5 billion times the mass of our Sun. And so our next task is to estimate the entropy of this beast. To do that, we can take our black hole entropy equation and rewrite it in terms of the mass of our Sun. If we then take the mass of the M87 supermassive black hole to be roughly 6.5 times 10 to the power of 9 times the mass of our Sun, and sub this into the entropy equation, we find a value of around 4 times 10 to the power 96 times Boltzmann's constant for the entropy. A truly mind-bending number, greater than the entropy of the entire universe near the Big Bang. And this isn't the only supermassive black hole that's been imaged. If we take our own galaxy, the Milky Way, and peer into the centre, we find the supermassive black hole Sagittarius A star, with a relatively modest mass of around 4 million times the mass of our Sun. And if we then sub this into our entropy equation, we find a value of around 2 times 10 to the power of 90 times Boltzmann's constant, which is significantly smaller than M87's black hole, but still larger than the entire entropy of the universe at the Big Bang. And so the moral of the story is that supermassive black holes utterly dominate the entropy of the universe. So can we use this fact to estimate the entropy of the entire observable universe today? Well, yes we can, because observations in astrophysics suggest that almost every large galaxy in the universe hosts a supermassive black hole at its centre, with a typical mass of around 10 to the power 8 times the mass of our Sun. And since there are of order 10 to the power 12 galaxies in the observable universe, by multiplying the average supermassive black hole entropy by the total number of galaxies, we find a value of around 10 to the power of 105 times Boltzmann's constant. More careful and precise calculations using the observed mass distribution of supermassive black holes gives a value closer to 10 to the power of 104 times Boltzmann's constant. So we can now begin to see the big picture emerge. As we've seen, the early universe, soon after the Big Bang, had an entropy of order 10 to the 89 times Boltzmann's constant, dominated by smooth thermal radiation, whereas the universe today has an entropy of order 10 to the power of 104 times Boltzmann's constant, dominated by supermassive black holes. And importantly, we see that the entropy really has increased enormously, and this is in agreement with the second law of thermodynamics. Okay, but what about the future of our universe? Can entropy keep on increasing indefinitely, or is there a maximum possible entropy that our universe can have? Well, gravity gives a very clear answer. Maximum entropy would be achieved if we collapsed everything in the universe into one gigantic black hole containing essentially all the mass in our patch of the universe. That configuration has, by far, the largest entropy gravity allows. So let's estimate it. We've already written down an expression for the entropy of a black hole in terms of its mass, m. The next step is to take m to be the mass contained in the observable universe. If we count just the ordinary matter, the stuff made of atoms, that mass is estimated to be around 1.5 times 10 to the power 53 kilograms. If you then sub this value into the entropy equation, you find that the maximum possible entropy comes out at around 10 to the power of 123 times Boltzmann's constant. That's the entropy you'd get if you took all the atomic mass in our observable patch and collapsed it into a single gigantic black hole. And even if you include dark matter as well, you only change this by an order of magnitude. The headline number stays essentially the same. Okay, now compare that with what we actually had near the beginning of the universe, near the Big Bang. The early universe's entropy, dominated by smooth thermal radiation, was about 10 to the power 89 times Boltzmann's constant. So in gravitational terms, the early universe wasn't just low entropy, it was absurdly, fantastically, unbelievably low entropy compared to what was available. It sat roughly 34 orders of magnitude below the maximum value. Smooth, uniform, and with almost all the gravitational entropy still waiting in the future. And so that raises another question. What was the likelihood that our universe, just by chance, started in such an extraordinarily low entropy state? Well, if you want to answer that question and determine how special a state it is, you don't really ask for its absolute entropy. Rather, you ask, what fraction of all possible states does it represent? So let's calculate that for our universe. If the maximum entropy available is of order 10 to the power of 123 times Boltzmann's constant, then Boltzmann's entropy equation can be rearranged to estimate the corresponding number of compatible microstates. Next, consider the subset of states that correspond to the low entropy, smooth, gravitationally unclumped early phase of our universe at the Big Bang, and call the number of those states omega BB. Again, using Boltzmann's entropy equation and rearranging, we can estimate the number of microstates corresponding to the low entropy Big Bang macrostate. It then follows that the fraction of all allowed states that look like the low entropy Big Bang is simply the ratio omega BB divided by omega max. And if we sub in the expressions we just derived, we find the following expression. Now, we can neaten this up a bit by combining the exponential terms, and then to evaluate this expression, we simply need to sub in the values that we determined earlier. And now comes the key point. When we look at the difference, SBB minus Smax, and sub in the numbers, because the maximum entropy is 34 orders of magnitude larger than the entropy soon after the Big Bang, it utterly dominates. And we can essentially ignore the first term. And so we write SBB minus Smax is roughly equal to minus 10 to the power of 123 times Boltzmann's constant. And so, to an excellent approximation, our ratio F can be written as e to the minus 10 to the power of 123. And then finally, we can rewrite this in a more familiar power of 10 form by making use of the fact that e to the power x is equal to 10 to the power of x divided by log 10. In which case, we can write e to the power of minus 10 to the power of 123 as 1 over 10 to the power of 10 to the power of 123 over log 10. In popular accounts and in Penrose's own shorthand, you'll often see this quoted schematically as roughly 1 over 10 to the power of 10 to the power of 123. And that's the famous headline form, first estimated by the Nobel Prize-winning physicist Roger Penrose, 1 part in 10 to the power of 10 to the power of 123. This is a number so extreme that writing it out in full would require more zeros than there are particles in the observable universe by about 10 million trillion times. And this is Penrose's point. If you pick a gravitational state at random, with each microstate weighted equally, from all the states compatible with our universe's mass energy, the chance of getting anything like our smooth low entropy Big Bang is not 1 in a million, or 1 in a trillion, or even 1 in 10 to the power of 100. It's roughly 1 in 10 to the power of 10 to the power of 123, which means that the initial state of our universe was not just special, it was special beyond anything ordinary intuition can handle. And ultimately, that helps us answer the question we started this video with. If the laws of physics don't care which way time runs, why does time in our universe so clearly have a direction? The answer led us to entropy, and entropy led us back to the beginning of the universe. We found that the early universe, despite being hot, dense, and full of radiation, had an entropy of only about 10 to the power 89 times Boltzmann's constant. That sounded huge, but gravity changed the game. When you include gravity, we found that the entropy of the universe today is dominated by supermassive black holes with a combined value of around 10 to the power of 104 times Boltzmann's constant. And even that pales into insignificance compared to the maximum possible entropy of around 10 to the power 123 times Boltzmann's constant. And that's why entropy has been able to increase. That's why the second law holds. And that's why time has an arrow. Because of gravity and its impact on entropy. But Penrose's argument also reveals something far more unsettling. Compared to what was possible, the initial state of our universe was extraordinarily special, roughly 1 part in 10 to the power of 10 to the power of 123. And so this raises a new, important, and still unanswered question. Why was the Big Bang so special? Was it pure chance? Or was it something to do with inflation or quantum gravity or the structure of space-time itself? Or was it finely tuned by some creator? Or are we still missing the right way to even think about the initial conditions of the universe? That's the mystery at the heart of the Big Bang. And perhaps someone watching this video may one day be able to shed some light on one of the great unsolved problems in physics. And in the next video in this series, we're going to start exploring the ideas physicists have proposed to answer it, and why, so far, none of them are completely satisfying. But for now, thank you for watching, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much. I couldn't do it without you.